The discussion that we had in the last video about the Neyman Pearson paradigm may be conveniently couched in terms of a single quantity, namely the probability of rejecting H0. We can express everything in terms of just probability of rejecting H0, because if H0 is true, then this quantity is just probability of type 1 error, rejecting H0 when H0 is true. And if H1 is true, in that case this is the power, that is 1 minus type 2 error, probability of rejecting H0 when H1 is true. So in both the cases, we can talk about only probability of rejecting H0. So the entire discussion may be represented using a graph like this. In the graph, the y-axis shows the probability of rejecting H0, and the x-axis shows the parameter space. In our case, we are working with simple hypothesis. So both H0 and H1 merely denote 2 points on this x-axis. Then probability of rejecting null hypothesis are like just 2 points. So probability of rejecting the null hypothesis when H0 is true is denoted by this height, and the same probability when H1 is true is denoted by this. So in our last example, you might think of this as 0.5 and this as 0.7. This is where I am showing the parameter P. It can take only 2 possible values. Now, what are we exactly trying to get? We want to keep probability of type 1 error small and power as high as possible. Making power as high as possible means keeping probability of type 2 error as small as possible. So I want this point to be as low as possible and this to be as high as possible. This is of course scale from 0 to 1. Now, as I have already mentioned, usually probability of type 1 and probability of type 2, they cannot be changed independently. So if you reduce one, generally the other also goes down. I'm sorry, I just made the wrong statement. If you reduce one, the other goes up. And if you increase one, the other goes down. So in this case, whenever you reduce probability of type 1 error, that is whenever you bring this point down, that point also tends to come down. They both go up and down more or less together. It's not that they will always have the same value or anything, but if you take various reasonable tests, if this is low, then this will also tend to be low. Now suppose I get a test like this. So suppose someone comes up with a different test, the green test, where I see this point is below and that point is above, then of course we will prefer the green test, because this gives me more power and less probability of type 1 error. However, if we have a situation like this where you are getting more type 1 error, but at the same time we are getting more power, then it becomes difficult to decide how we should choose between, say, the blue one and the green one. And the way Neyman Pearson suggested that we solve the problem is by putting an upper bound on probability of type 1 error, that is, we put a line like this, and we consider only the tests that fall below this line. Remember, the line is only for H0, not on this line. So in this case, the blue test is automatically ruled out. Then all the tests that will allow the probability of type 1 error to be below that line, among all those things, look at that one where the point is the highest possible in this line. In this case, it is the green test, and you go for the green test, and that we call the most powerful test of this particular level. This is what we have already seen in our last video. It was just a recap. Now the discussion so far revolved around the situation where both H0 and H1 were simple hypotheses. That is, they both specified a single value of the parameter as a result, our parameter space was just a doubleton set, like P is either 0.7 or 0.5. Now that is of course not a very natural situation. A more natural situation is where the parameter space contains possibly infinitely many values, and you partition all those values into two parts. H0 takes charge of one part and H1 takes charge of the other part. In this case, the same graphical representation will take the slightly different form like this. We still have probability of rejection, rejecting the null hypothesis on the y-axis, but now this is the entire parameter space which I have split at some point. So it is something like say 0 to 1, and this may be half, and you say H0 says that the probability is less than or equal to half, and H1 says it is greater than half. Of course, it does not have to be two such intervals. It could be you are testing that the coin is unbiased versus the coin is biased, in which case H0 is just the point at half and H1 will be on both sides of it, so it will be union of two intervals. But for explanation purposes, I will focus on this particular setup. Now, when you are in this situation, remember that you no more have probability of rejecting your null hypothesis as a single point. It now takes the form of a graph. There is no reason why it should be a continuous graph. You might think of pathological examples where it will be discontinuous, but in most cases it will be a continuous graph, because remember, the test is based without any prior knowledge of whether H0 is true or H1 is true, so its behavior should be kind of continuous when you move from H0 to H1. And you are taking some kind of an averaging thing when you are finding probability, so that will also have a smoothing effect. So more often than not, the curve will be a continuous smooth curve like this. So part of the curve is on H0 and part of the curve is on H1. And this poses two different problems to the Neyman Pearson paradigm. Neyman Pearson paradigm said that I want to keep probability of type 1 error low. Now, what is meant by probability of type 1 error? It is not just a number. For different values of theta under H0, you have different probabilities of type 1 error. Which one are you trying to keep under that threshold? Well, this problem is easily resolved. We want to keep all the values under a threshold. So we put a threshold like this. We just put a threshold like this. And we want the entire purple portion of the curve to be under that. For example, if you come up with some test where the purple portion of the curve shoots above this bound, to some extent, we shall not consider such a test. So when we put an upper bound, we want this upper bound to be maintained all throughout H0. So the first problem is easily remedied. So the Neyman Pearson paradigm is again slightly updated to say if H0 happens to be a composite hypothesis, make sure probability of type 1 is always below that pre-specified threshold for all values of theta under H0. However, there is a more formidable problem that comes up when we look at H1. We want to say that this green curve should be as high as possible. Suppose we have a green curve like this. So in this case, both the purple parts are below the threshold, so both are within our valid domain of discourse. So these are valid tests. Now for one of them, the curve, the green part is above the other. For the remaining part, that part is above. So you cannot say that either this test has higher power or that test has higher power. Sometimes this has higher power and sometimes that has higher power. Maximizing numbers is easy. You can always compare two numbers. Either they're equal or one is larger and the other is smaller. But if you are working with functions, they may be partly larger and partly smaller. So how do we really compare them? And that is a more formidable problem presented to this Neyman Pearson paradigm when you are working with composite H1. Now this problem is a serious one, and there is no simple answer to this question unless you happen to be a very special situation like this. So suppose you have this special situation where you have got these 3 tests, and all of them are under the bound in the H0 part. But here, as we have already seen, these 2 curves are fighting with each other. However, there is one test which dominates everybody. I do not care what happens here as long as the purple part remains below the bound. But over H1, this is always above every other possible curve which satisfy the same bound. If you can find such a thing, then of course Neyman Pearson paradigm will suggest that you go for this particular test. But there is no guarantee that such a thing will exist. If such a thing exists, we call it uniformly most powerful test, because of the obvious reason that this is most powerful and it maintains its most powerful property uniformly throughout H1. So we call it uniformly most powerful test, or UMP test. If you are working over H1, which is simple, then you just call it MP test for most powerful, and if it is composite, you are calling it UMP. However, if you do not have any such test, then life is rather complicated, and Neyman Pearson paradigm basically falls flat. So what do you do in that case? Well, there is no regular answer to that question. What people do is that they try to impose further restrictions on the class of tests that you are considering. For example, there is a class of test called unbiased tests. That is something that we are not going to go into right in this video, but just imagine that there is a subset of tests, all possible tests, which are good with respect to some criterion. It's called unbiased tests. Then they say that, well, focus your attention to only the unbiased tests and try to see if restricted to that subclass the Neyman Pearson paradigm works. That is, you can find something in that subclass which is uniformly most powerful within that subclass. If you can find such a thing, then again you are happy. You do not call it UMP test anymore, you call it uniformly most powerful unbiased test, UMPU test. So that is the idea. You focus your attention only on suitable subclasses and hope that you will get a most powerful test satisfying that type 1 bound within that subclass. And if that doesn't work, then you look for some other subclass. For example, some people will say, well, I really do not want that uniform property. There is some particular value of the parameter which I believe is more important than the other values. So as long as my test beats others over a neighborhood of that specific point, I am happy. Then we call it a locally most powerful test, locally around that point. And generally, whenever you are working with that local point is typically taken to be this point. So this is sort of the junction point, and this is where you are most tense or nervous about whether your test is going to perform well, because it is just the border region. It is just like the tension that exists in the border of India and Pakistan. So if it is far out into H1, you have no problem. Far out inside H0, no problem. But the border region is where you are worried about. So you often go for tests that will beat the other tests over a neighborhood of this. So you take a neighborhood of this point in the H1 side, not on the H0 side. And if you have a test that beats everyone over that neighborhood, you call it a locally most powerful test. As a result, you have concepts like UMPU test, uniformly most powerful unbiased test, UMPI test, uniformly most powerful invariant test. Invariant test is yet another class of test which is desirable in certain conditions. You have LMP test, locally most powerful test. You have LMPU test, locally most powerful among all unbiased tests. You have LMPI test, locally most powerful among all invariant tests, and you can put restriction after restriction, but naturally the more restrictions you put, the less interesting the result is. just as if I say, I am the best teacher in ISI, that's an interesting statement. But if I say, well, I am the best teacher in ISI among all teachers whose first name starts with A and last name starts with C and who are exactly 5 feet 9 inches tall, of course, then the statement will be true. But I am basically restricting the set in such a way so that I can call myself the best teacher. The more restrictions I put, less interesting is the final outcome. So, while people do put all such restrictions, and there are some papers written on those things, these are not really interesting. So, if UMP test exists, that is great news. If not, people will go for UMPU test. We have not yet discussed unbiased test, but if you already know unbiased test, you will understand what it is. So, UMP is great. UMPU is reasonable relaxation of that, and the other things just do not cut the mark. So we will say that the Neyman Pearson paradigm essentially fails in those cases.